Last month, our anomaly detection system flagged an unusual pattern in server traffic at 2 a.m. What seemed like a minor blip turned out to be the early signs of a major security breach that could have exposed customer data. The system that caught it wasn't magic. It was a carefully engineered pipeline. Through this video, I'll walk you through building that same anomaly detection pipeline from scratch, starting with the fundamental challenge every data scientist faces. How do you actually define what's normal in your data? We'll progress through each critical stage, measuring performance at every step. What if I told you that the hardest part of anomaly detection isn't building the model? It's defining what normal even means. Let's imagine you're monitoring a manufacturing production line. Your sensors are collecting thousands of data points every minute on temperature, pressure, vibration, and dozens of other metrics. Everything seems to be running smoothly until suddenly an alert triggers. A critical component is showing unusual behavior. But is it truly anomalous or just a natural variation in the manufacturing process? This scenario highlights the fundamental challenge that sits at the heart of every anomaly detection system, establishing a reliable baseline of normality in your data. It sounds straightforward, but in practice, it creates a fascinating paradox that confounds even the most sophisticated systems. To detect an anomaly, you first need to understand what constitutes normal behavior. But to define normal behavior, you need to identify and exclude anomalies from your analysis. It's a circular problem, one that requires nuanced thinking to solve. Let's start by clarifying an important distinction that's often overlooked. Anomalies and outliers aren't the same thing, despite being used interchangeably in casual conversation. Anomalies represent meaningful deviations from expected patterns. They carry significance and warrant investigation. They're the signals hiding in your data. Outliers, on the other hand, often represent statistical noise, data points that deviate from the norm but don't necessarily contain valuable information. Consider a financial fraud detection system. A sudden $10,000 transaction from an account that typically sees $50 purchases would be flagged as an anomaly because it represents a meaningful deviation that could indicate fraud. Meanwhile, a one-time $75 purchase might register as a statistical outlier when compared to the usual $50 transactions, but doesn't necessarily indicate fraudulent activity. It's just normal variation in consumer behavior. What makes this distinction particularly challenging is that normal behavior isn't universal. It's highly contextual and domain-specific. This contextual nature of normality creates a moving target for anomaly detection systems. Take network traffic as an example. The definition of normal traffic for an e-commerce server at 2 p.m. on a regular Tuesday looks dramatically different from what's normal at 8 p.m. on Black Friday. During business hours on a weekday, you might expect a steady flow of traffic with predictable patterns, but during a major shopping event, a massive spike in traffic that would trigger alarms on any other day is perfectly normal and expected. This time context is critical for defining normality, but it gets even more complex. Imagine you're responsible for monitoring a data center. What constitutes normal CPU utilization? Is it 30%, 50%, 80%? The answer depends not just on the time of day, but on the specific server's role, the applications it's running, the business cycle, and dozens of other factors. Without understanding these contextual elements, your anomaly detection system will either miss critical issues or flood you with false alarms. The challenge becomes especially pronounced when dealing with time series data, where values change over time in patterns that themselves can evolve. Time series data introduces unique complexities because normal behavior must account for multiple interacting components. Consider seasonal retail sales data. A sudden 300% increase in transactions during December isn't an anomaly, it's an expected seasonal pattern. Your definition of normality must incorporate this seasonality or risk flagging legitimate holiday shopping as anomalous. Similarly, A steadily increasing trend in user signups for a growing startup isn't anomalous. It's a positive indicator of business growth. Yet many naive detection systems would flag this trend as unusual behavior because it deviates from historical averages. To understand how these components interact, imagine visualizing a year of hourly traffic to a restaurant's website. You'd likely see daily patterns, peaks during lunch and dinner hours, weekly patterns, higher traffic on weekends, and seasonal patterns, holiday spikes. What's normal at any given moment depends on where you are within these overlapping cycles. Even more challenging, these patterns themselves can change. A restaurant that introduces a popular new weekend brunch might see its weekly pattern shift dramatically. Is this new pattern an anomaly or a new normal? The answer depends entirely on context that pure statistical methods might miss. This multidimensional nature of time series data, with its blend of trend, seasonality, and random noise, creates a significant challenge for establishing baseline normality. A single approach doesn't work across all scenarios. So how do we solve this circular problem systematically? How do we define normal behavior when normal itself is a moving target? The solution requires a deep understanding of your data's inherent patterns before applying any algorithms. It's about taking the time to analyze the underlying structure of your dataset, identifying seasonal variations, recognizing trends, and understanding the domain context in which the data exists. For time series data, this might involve decomposition techniques that separate your data into trend, seasonal, and residual components. By isolating these elements, you can define normality for each component separately, creating a more nuanced understanding of what normal really means in your specific context. Domain expertise plays a crucial role here as well. A medical professional reviewing patient vital signs knows that what's normal for a 25-year-old athlete differs dramatically from what's normal for an 80-year-old with chronic conditions. This domain knowledge must be encoded into your anomaly detection system through carefully selected features, appropriate data transformations, and thoughtful model selection. The most effective approach often combines statistical analysis with domain expertise in an iterative process. You start with a basic definition of normality based on historical patterns, then refine it as you gain more insights from both the data and domain experts. This refinement process helps you distinguish between real anomalies that require attention and expected variations that should be incorporated into your baseline. Ultimately, defining normality requires acknowledging that it's not a static concept, but a dynamic one that evolves with your data. The most sophisticated anomaly detection systems embrace this reality, continuously updating their understanding of normal behavior as new patterns emerge. This adaptability is what separates truly effective anomaly detection systems from those that drown in false positives or miss critical outliers. By building a robust understanding of what constitutes normal behavior in your specific context, you create the foundation for accurate anomaly detection that delivers genuine value. The value of a well-tuned anomaly detection system extends far beyond abstract data science principles. Across manufacturing, finance, healthcare, and cybersecurity, organizations implementing these systems are witnessing transformations that challenge conventional wisdom about what's possible, with some reporting up to 60% improvement in critical metrics that directly impact both human lives and financial outcomes. When we talk about anomaly detection applications, not all use cases are created equal. In some contexts, detecting unusual patterns might simply improve efficiency or provide interesting insights. But in mission-critical environments, the same technology becomes a lifeline where minutes, sometimes even seconds, can separate a minor incident from catastrophic failure. Manufacturing stands at the forefront of this revolution. Factory floors once relied on scheduled maintenance and reactive repairs, but today's smart facilities deploy sensors throughout production lines that continuously monitor equipment health. These systems track subtle changes in machine vibration patterns, temperature fluctuations, and operational parameters that humans simply cannot perceive. The impact? A remarkable 40% reduction in unplanned downtime across facilities that implement these predictive maintenance systems. Consider what this means in practical terms. A typical automotive manufacturing plant can lose between $15,000 and $50,000 per minute of downtime. When a critical assembly line unexpectedly fails, the costs cascade rapidly throughout the entire operation. Workers stand idle, shipping schedules collapse, and customer commitments fall into jeopardy. By identifying anomalous behavior in equipment days or even weeks before traditional methods would detect a problem, these systems transform maintenance from reactive scrambling to carefully planned interventions. The financial services industry faces a different but equally critical challenge. Here, anomaly detection operates in the realm of milliseconds, where transaction processing systems must evaluate thousands of activities per second to distinguish legitimate customer behavior from fraudulent attacks. The sheer volume makes human monitoring impossible. You need algorithms that can instantly recognize when a pattern breaks from established norms. What makes this particularly challenging is the constant evolution of both normal consumer behavior and fraudulent techniques. A customer traveling internationally might suddenly make purchases from unusual locations, triggering false alerts. Meanwhile, sophisticated fraud rings craft attacks specifically designed to mimic typical consumer behavior. Despite these challenges, financial institutions implementing advanced anomaly detection systems have achieved a 60% improvement in fraud detection rates while simultaneously reducing false positives that frustrate legitimate customers. The stakes climb even higher in healthcare, where anomaly detection literally saves lives. Modern hospital systems continuously monitor patient vital signs, generating massive data streams that contain subtle patterns imperceptible to even the most attentive medical professionals. Advanced algorithms can detect deviations from patient-specific baselines hours before traditional monitoring systems would trigger alerts. Early warning systems built on these principles have improved patient outcomes by 30% in critical care environments. Take sepsis, for instance, a life-threatening condition where the body's response to infection damages its own tissues. Traditional detection methods often identify sepsis only after it has progressed significantly. Anomaly detection systems can spot the subtle changes in vital sign patterns that precede full-blown sepsis, allowing medical teams to intervene when treatments are most effective. Cybersecurity presents yet another frontier where anomaly detection proves transformative. Traditional security approaches relied heavily on signature-based systems. Essentially cataloging known attacks and watching for their specific characteristics, this approach fails entirely against novel attacks and zero-day exploits that haven't been seen before. Behavioral anomaly detection takes a fundamentally different approach. Rather than looking for known bad patterns, these systems build baselines of normal network traffic and system behavior, then flag deviations for investigation. This paradigm shift enables security teams to identify sophisticated attacks that deliberately avoid triggering traditional defenses. An employee account suddenly accessing unusual database servers at 3 a.m., a workstation transferring data to previously unseen external domains, or authentication attempts occurring in impossible geographic sequences. These behavioral anomalies often reveal breaches that would otherwise remain hidden for months. What connects these diverse applications is their shared requirement for systems that can adapt to continuously evolving definitions of normal. In manufacturing, seasonal production changes create new baseline vibration patterns. In finance, consumer spending habits shift with economic conditions and trends. Healthcare baselines must account for patient-specific factors and treatment responses. And in cybersecurity, network traffic patterns change as organizations adopt new technologies and work patterns. Static models quickly become obsolete in these dynamic environments. The most effective systems incorporate continuous learning mechanisms that recognize when baseline patterns themselves are shifting. This adaptability differentiates truly valuable anomaly detection from systems that gradually degrade into noise generators as conditions evolve away from their initial training data. The return on investment across these industries tells a compelling story. Manufacturing facilities report not just the 40% reduction in unplanned downtime, but also extended equipment lifespans and optimized maintenance scheduling that reduces parts inventory costs. Financial institutions measuring the 60% improvement in fraud detection translate this into millions of dollars in prevented losses annually. Healthcare facilities see reduced lengths of stay and improved resource utilization alongside the 30% improvement in patient outcomes. And cybersecurity teams report detecting breaches weeks or months earlier than was previously possible, dramatically reducing data exposure and remediation costs. Perhaps most tellingly, organizations at the forefront of anomaly detection implementation are now building cross-functional teams that span data science, domain expertise, and operational departments. They recognize that the technology's value emerges from the intersection of algorithmic sophistication and deep domain knowledge. Neither is sufficient alone. A manufacturing engineer who understands exactly how vibration patterns change when a specific bearing begins to fail can help data scientists tune models to focus on the most relevant signals. A veteran fraud analyst who recognizes the subtle patterns of emerging fraud techniques provides invaluable input to financial anomaly detection systems. Clinical specialists help healthcare data teams understand which combinations of vital sign changes deserve heightened scrutiny, and experienced security analysts help cybersecurity systems distinguish between benign anomalies and genuinely suspicious behavior. Domain expertise shapes how we interpret anomalies, but beneath every successful implementation lies a secret that few discuss. The difference between systems that deliver those impressive 30 to 60% improvements and those that generate endless false alarms isn't just algorithm choice, it's an intricate pipeline where multiple distinct components must work in perfect harmony. When organizations invest in anomaly detection, they often focus disproportionately on selecting the perfect algorithm. They'll spend weeks evaluating isolation forests against autoencoders or debating the merits of various clustering techniques. But here's what experienced practitioners understand. Even the most sophisticated algorithm will fail spectacularly when implemented in isolation. Think of an anomaly detection system as an orchestra rather than a solo performer. Each component plays a critical role, and weaknesses in any single element compromise the entire performance. This orchestration begins long before any model training occurs, with the crucial first step of data ingestion. The data ingestion phase sets the foundation for everything that follows. Here, raw data from various sources, sensors, transaction logs, network monitors, is collected, standardized, and prepared for further processing. This seemingly mundane stage actually determines the ceiling of what your system can achieve. Missing values must be handled through imputation or exclusion. Outliers require special consideration. Are they noise to be removed or potential anomalies to preserve? Time synchronization becomes critical when working with multiple data streams. A millisecond misalignment can generate phantom anomalies that don't actually exist. Consider a manufacturing system monitoring equipment vibration. If sensors occasionally drop readings during high vibration events, precisely when failures are most likely to occur, Your data ingestion pipeline must recognize and account for this systematic bias. Otherwise, you'll build a detector that misses the very events it was designed to catch. Once your data is properly collected and cleaned, the next critical component enters: feature engineering. This transformative stage converts raw data into meaningful representations that amplify the signal of anomalies while suppressing background noise. Feature engineering is where domain knowledge and data science expertise intersect to create powerful detection capabilities. Raw measurements rarely tell the complete story. In network security, a single unusual connection might not indicate an attack, but the pattern of connections over time could reveal a data exfiltration attempt. Feature engineering captures these higher order patterns through techniques like rolling statistics, frequency domain transformations, and contextual embeddings. For univariate data, this might involve calculating moving averages or variance. For multivariate data, correlation metrics between different variables often reveal subtle anomalies invisible when examining each variable in isolation. The art of feature engineering lies in creating representations that make anomalies more detectable. A skilled practitioner might transform vibration measurements into frequency spectra, knowing that bearing failures show distinctive spectral signatures long before amplitude changes become apparent. Or they might calculate ratios between related metrics, knowing that while both CPU and memory usage fluctuate naturally, their ratio remains relatively stable during normal operation. Only after these foundational stages do we arrive at the modeling component, the part that receives disproportionate attention in most discussions of anomaly detection. Here, algorithms are selected and trained based on both data characteristics and operational requirements. The appropriate choice depends on factors like data dimensionality, expected anomaly frequency, and available computational resources. What many fail to recognize is how deeply intertwined the modeling component is with earlier pipeline stages. A beautifully engineered feature space can make even simple statistical methods highly effective. Conversely, poor feature engineering necessitates increasingly complex models to compensate. Models that are harder to interpret, more computationally expensive, and often less robust in production environments. The modeling component must also align with your operational context. Will detection occur in batches or real time? Are explanations required for each flagged anomaly? How quickly must the model adapt to evolving patterns of normality? These questions shape algorithmic selection far more than abstract performance metrics on benchmark datasets. Following model training comes the equally critical evaluation component. Contrary to common practice, simple accuracy is rarely an appropriate metric for anomaly detection systems. The inherent imbalance between normal and anomalous observations requires more nuanced evaluation approaches. Precision measures the proportion of flagged anomalies that are genuine, while recall captures the percentage of actual anomalies successfully detected. The F1 score provides a balanced measure combining both metrics, while the area under the ROC curve, AUC, evaluates detection performance across different threshold settings. Proper evaluation requires careful consideration of your specific operational context. In some scenarios, missing a single critical anomaly could be catastrophic, making recall the priority metric. In others, false positives generate significant operational costs, elevating the importance of precision. The evaluation component isn't merely about measuring system performance, it's about aligning that performance with your organization's specific needs and constraints. These four components, data ingestion, feature engineering, modeling, and evaluation, form the core of any effective anomaly detection pipeline. But their power emerges not from individual excellence, but from their seamless integration. A change in one component ripples through the entire system. Modify your feature engineering approach, and you may need to recalibrate your model parameters, adjust your evaluation metrics, and you might reconsider your entire modeling strategy. Visualizing this pipeline helps clarify its interconnected nature. Imagine a flowchart where raw data enters through ingestion processes, transforms through feature engineering, feeds into modeling components, and exits through evaluation frameworks. At each junction, information flows not just forward but backward through feedback loops. Evaluation results inform model refinement. Model performance guides feature engineering adjustments, and feature engineering needs shape data collection strategies. This visualization reveals why weakness in any component compromises the entire system. When anomaly detection projects fail, the root cause rarely lies in algorithm selection. More commonly, the failure stems from neglecting one of these core pipeline components or failing to ensure their cohesive integration. Data scientists accustomed to supervised learning sometimes underestimate the importance of feature engineering for anomaly detection. Engineers familiar with rule-based systems might neglect rigorous evaluation protocols, and both might overlook the critical importance of data quality at the ingestion stage. Building an effective anomaly detection system requires a holistic approach, one that considers each component in relation to the others and to the specific operational context where the system will function. This comprehensive perspective distinguishes mature implementations from naive algorithm applications, explaining the vast performance gap between systems that merely detect statistical outliers and those that identify meaningful anomalies worth investigating. The paradox at the core of anomaly detection is that the most valuable anomalies to detect are often those we've never seen before, yet traditional machine learning excels at finding patterns it has previously encountered. This fundamental tension between supervised and unsupervised approaches forces organizations into a critical strategic decision that shapes their entire detection capability. When building an anomaly detection system, you'll inevitably face this crossroads. Do you train your models on labeled examples of anomalies, or do you build systems that can identify deviations without ever seeing an example of what wrong looks like? This isn't just a technical choice, it's a philosophical one that determines what kinds of threats your system can identify and what blind spots it might have. Supervised approaches require something that's surprisingly scarce in many organizations: labeled examples of anomalies. Think about it. In many domains, genuine anomalies are rare by definition. A manufacturing line might run for months without a critical failure, and when failures do occur, they may manifest in different ways each time. This creates an inherent data imbalance that challenges traditional classification algorithms. When you do have sufficient labeled data, supervised methods shine at detecting specific types of known anomalies with high precision. They can learn the exact signatures of equipment failures, fraudulent transactions, or network intrusions that they've seen before, but therein lies their limitation. They excel at finding what you already know to look for, not at discovering novel threats or failure modes. What happens when a new type of credit card fraud emerges, one that doesn't match any pattern in your training data? This is where supervised systems often fail spectacularly, creating dangerous blind spots in your detection capabilities. Unsupervised approaches tackle the problem from an entirely different angle. Rather than requiring examples of anomalies, they build models of normal behavior and flag deviations from that norm. Clustering algorithms group similar data points together, density estimation methods model the probability distribution of normal data, and distance-based techniques measure how far observations lie from the majority. The beauty of these approaches is their ability to detect the unknown, patterns that deviate from normality in ways you never anticipated. When Telefonica needed to analyze streaming network data for threats, they transitioned from supervised to unsupervised models based on LSTM networks. This shift freed them from the constraints of limited labeled data and enabled them to identify novel attack patterns that wouldn't have been caught by signature-based approaches. But unsupervised methods aren't without their challenges. Without labels to guide them, these algorithms sometimes struggle to distinguish between meaningful anomalies and benign statistical outliers, potentially generating more false positives. They also typically require careful tuning of sensitivity thresholds to balance detection capabilities against alert fatigue. Between these two approaches lies a compelling middle ground: semi-supervised methods. These techniques primarily train on examples of normal data to build a model of what normal looks like, then flag deviations as potential anomalies. This approach requires far fewer labeled examples than fully supervised methods and often delivers more precise results than purely unsupervised techniques. The performance differences between these approaches can be dramatic. In a comparative study involving diverse anomaly types, unsupervised methods achieved an impressive recall of 0.92, meaning they found 92% of actual anomalies. Supervised methods, hamstrung by insufficient labeled examples of certain anomaly types, performed significantly worse in detecting novel anomalies not represented in their training data. Consider a real-world example from network security monitoring. When analyzing network traffic for potential intrusions, a supervised system trained on known attack signatures might achieve near-perfect precision in detecting those specific attacks. But what about zero-day exploits that don't match any known signature? An unsupervised system monitoring for unusual network behavior patterns might catch these novel threats, even if it occasionally flags some benign but unusual traffic patterns as well. Or take manufacturing quality control. A supervised system trained on examples of specific defects will reliably catch those exact issues, but might miss a new type of defect caused by a recently degraded component. An unsupervised system monitoring overall product characteristics would flag any significant deviation from normal production patterns, potentially catching the new defect type before it affects thousands of units. The choice between these approaches isn't just academic, it's driven by practical organizational constraints. Does your organization have access to labeled examples of anomalies? How comprehensive is that labeled dataset compared to the variety of anomalies you might encounter in production? Can you tolerate some false positives to gain the ability to detect completely novel anomalies? The answers to these questions form the foundation of a decision framework for selecting your approach. When labeled anomaly data is abundant and representative of the full range of anomalies you expect to encounter, supervised approaches offer high precision and recall for those specific anomaly types. This scenario is common in mature security monitoring systems with extensive historical data on attacks and intrusions. When labeled data is scarce, or when detecting novel, previously unseen anomalies is critical, unsupervised approaches provide the flexibility to identify deviations without requiring examples of every possible anomaly type. This is particularly valuable in environments where new threats or failure modes emerge regularly. When you have abundant examples of normal behavior but limited examples of anomalies, semi-supervised approaches offer an effective middle ground, learning primarily from normal data while using the limited anomaly examples to fine-tune decision boundaries. The most sophisticated systems often employ hybrid approaches using supervised methods to catch known anomaly types with high precision while running unsupervised methods in parallel to detect novel deviations that might indicate emerging threats. The benchmark performance of these different approaches can vary significantly based on the specific characteristics of your data. In a comprehensive evaluation across 67 different real-world datasets of production traffic, ensemble models combining multiple approaches achieved the highest overall performance with a recall of 0.92. Meanwhile, lightweight LSTM-based forecasters achieved a respectable recall of 0.85, but with lower precision, representing a different point on the performance trade-off curve. What's particularly interesting is how performance varies across different anomaly types. Supervised methods typically excel at point anomalies, individual data points that clearly deviate from normal values. Unsupervised methods often have an edge in detecting contextual anomalies where values are anomalous only in specific contexts, and collective anomalies where sequences of observations deviate from expected patterns. Your choice of approach should also consider operational constraints beyond just detection performance. Computational resources, the need for model interpretability, and the ability to adapt to changing data patterns all influence which approach will succeed in your specific environment. While selecting the right detection approach is crucial, have you considered what happens when your system must make decisions in milliseconds rather than hours? The timing requirements of your application create a fundamental divide in anomaly detection architecture, forcing a choice that dramatically impacts both what you can detect and how you respond. This timing dimension is about more than just operational convenience. It's about the very nature of what your system can accomplish. The difference between batch and real-time processing represents perhaps the most consequential architectural decision you'll make when designing an anomaly detection pipeline. Batch processing takes place after the fact, examining complete datasets with the benefit of hindsight. This retrospective approach allows for thorough, iterative analysis without the pressure of immediate decision-making. When you process yesterday's manufacturing quality data, last month's financial transactions, or last quarter's customer behavior patterns, you're operating in batch mode. For data scientists, this means that technical competence alone is insufficient. The advantages here are substantial. With complete datasets at your disposal, you can run sophisticated algorithms that might be too computationally intensive for real-time applications. You can perform multiple passes over the data, refining your analysis with each iteration. You can even manually validate results before taking action. This deliberate approach typically yields fewer false positives, a critical advantage when you're investigating rare anomalies that might otherwise be lost in the noise. Manufacturing quality control exemplifies effective batch processing. Engineers can analyze production data from completed shifts, identifying subtle patterns that might indicate emerging defects. Similarly, financial auditors review transaction histories to identify irregular patterns that warrant investigation. The common thread: time is a luxury these applications can afford. But what about scenarios where waiting isn't an option? Real-time processing exists in an entirely different operational reality. These systems must analyze data streams as they arrive, making split-second decisions under strict latency constraints. The credit card industry provides the perfect illustration. Fraud detection systems have exactly 3 seconds to determine whether a transaction is legitimate, not minutes, not hours, 3 seconds. This constraint isn't arbitrary. It represents the maximum acceptable delay in the customer experience before transaction approval. Similar time pressures exist across industries. Network security systems must identify intrusion attempts before attackers can extract sensitive data. IoT sensor networks monitoring critical infrastructure must detect failures before they cascade into catastrophic events. The computational challenges unique to real-time systems are formidable. Unlike batch processes that can leverage abundant computing resources, real-time systems operate under severe memory limitations. They can't store complete historical datasets for comparison. They can't run computationally intensive algorithms that might take minutes to complete. They can't pause for manual verification or reprocess data multiple times. Instead, these systems must employ incremental learning algorithms that can update their understanding of normal behavior without reprocessing everything that came before. They must make decisions based on limited context, often examining just the most recent observations rather than the entire historical record. Perhaps the most fascinating challenge these systems face is concept drift. when the definition of normal changes over time. Consider an e-commerce platform where user behavior gradually evolves as new features are introduced. A real-time anomaly detection system can't simply freeze its understanding of normal behavior. It must adapt continuously without the luxury of reprocessing the entire dataset from scratch. This adaptation requirement fundamentally reshapes algorithm selection. Techniques that excel in batch processing environments often falter when transplanted to real-time scenarios. The architectural patterns that enable effective real-time detection look remarkably different from their batch counterparts. Sliding window techniques form one crucial component of this architecture. Rather than processing all historical data, these approaches maintain a window of recent observations that moves forward in time as new data arrives. This allows systems to maintain awareness of recent patterns while keeping computational requirements manageable. As new data points enter the window, older ones exit, ensuring the system's view of normality evolves with changing behavior patterns. Stream processing frameworks provide the infrastructure backbone for real-time anomaly detection. Technologies like Apache Kafka and Apache Flink enable continuous analysis of data streams, processing each observation as it arrives rather than waiting to batch them together. These frameworks handle the complex plumbing of data movement, allowing detection algorithms to focus solely on identifying anomalies. When even standard algorithms prove too computationally intensive for real-time requirements, approximate algorithms offer a pragmatic alternative. These techniques deliberately trade perfect accuracy for processing speed, employing sampling methods to reduce the volume of data being analyzed. While they might miss subtle anomalies that more thorough approaches would catch, they deliver critical speed advantages that make real-time detection possible. The architecture required for real-time detection introduces another fascinating dimension: distributed processing. When dealing with high-volume data streams like network traffic or IoT sensor readings, the computational load often exceeds what a single machine can handle. Distributed architectures divide this workload across multiple nodes, each responsible for a portion of the detection task. This parallelization enables systems to maintain performance even as data volumes grow. Memory management becomes particularly critical in these distributed architectures. Unlike batch systems that can store vast datasets, real-time systems must carefully optimize their memory footprint. Techniques like feature hashing compress high-dimensional data into more manageable representations, while sketch algorithms provide statistical approximations without storing complete datasets. The balancing act between accuracy and speed creates fascinating engineering trade-offs. For instance, pre-processing steps that might improve detection accuracy in batch systems often prove too computationally expensive for real-time applications. Feature engineering must be streamlined to focus only on transformations that deliver substantial detection improvements with minimal computational cost. This constraint doesn't necessarily mean real-time systems are less effective, just differently optimized. They excel at rapid response to clear anomalies, often detecting and responding to threats faster than human analysts could ever manage. What they sacrifice in analytical depth, they gain in response speed. The most sophisticated anomaly detection architectures blend batch and real-time approaches into complementary systems. Real-time components provide immediate responses to clear anomalies, while batch processes perform deeper analysis to catch subtle patterns that faster systems might miss. This hybrid approach leverages the strengths of both paradigms while mitigating their weaknesses. Consider a network security application that employs real-time detection to block obvious attack patterns immediately, while simultaneously logging all traffic for more thorough overnight analysis. The batch component might identify subtle patterns indicative of advanced persistent threats, feeding these insights back into the real-time system to improve its detection capabilities for the following day. This feedback loop between batch and real-time components represents perhaps the most powerful architectural pattern in modern anomaly detection. Batch processes leverage their computational advantages to discover complex patterns, while real-time components apply these insights to immediate detection challenges. The result is a system that continuously improves while maintaining rapid response capabilities. Beyond architecture lies a deceptive adversary that doesn't announce itself with unusual values, but hides in plain sight within the natural rhythms of your data. Time series don't just flow forward, they pulse with seasonal patterns and drift with long-term trends that transform perfectly normal observations into apparent anomalies when your system lacks temporal intelligence. Did you know that naive detection systems misinterpret up to 75% of seasonal variations as threats? This isn't just inefficient, it's a fundamental breakdown that blinds your system to genuine anomalies hiding within expected fluctuations. Time series data presents unique challenges that standard tabular data approaches simply can't handle. Unlike static datasets where each observation stands independently, time series data contains intrinsic temporal structures that fundamentally alter what normal means from one moment to the next. These structures aren't random. They follow predictable patterns that your detection system must understand to function properly. Consider what happens when you ignore these temporal dynamics. A retail system that doesn't account for seasonal patterns might flag every holiday shopping surge as suspicious. A network monitoring tool might bombard you with alerts during predictable usage spikes every Monday morning. These aren't just minor inconveniences, they create a dangerous form of alert fatigue where analysts begin ignoring notifications entirely, including the truly critical ones. The problem stems from time series data's composite nature. Every observation contains multiple overlapping signals: the underlying trend, seasonal fluctuations at various frequencies, cyclical variations, and random noise. When we think about normal in this context, we must account for all these components simultaneously, a complexity that defeats simplistic detection approaches. Let's examine how we can systematically address these challenges, starting with trend detection. Trends represent the long-term directional movement in your data, the gradual increase in server loads as your user base grows, or the steady decline in manufacturing equipment performance as components wear. Identifying and removing these trends is essential because they can mask subtle anomalies or create false positives as the baseline shifts. A powerful approach for automatic trend detection involves interpolating between central parts of density metrics. This technique identifies the underlying directional movement without being overly influenced by outliers or short-term fluctuations. By fitting a smooth curve through your data's density centers, you can isolate and remove the trend component, creating what statisticians call a stationary time series, one where the statistical properties remain constant over time. Once trends are addressed, we must tackle the complex world of seasonality, those recurring patterns that appear at regular intervals. Seasonal patterns occur at multiple overlapping timescales: hourly server traffic patterns within days, weekly retail purchasing cycles, monthly billing cycles, and yearly holiday patterns. Each creates its own definition of normal that constantly shifts as these cycles progress. The autocorrelation function ACF provides a powerful tool for automatically detecting these periodic patterns. The ACF essentially measures how similar a time series is to itself at different time lags. When plotted, significant spikes above a predefined threshold reveal how strongly past values influence current ones, the hallmark of seasonal patterns. For instance, an ACF plot showing strong correlation at lag 24 in hourly data suggests a daily pattern, while spikes at lag 168 24/7 indicate weekly seasonality. This automated approach to periodicity detection eliminates guesswork and scales to handle thousands of metrics simultaneously. Instead of manually inspecting each time series, your system can automatically determine the appropriate seasonal adjustments needed for each metric, whether it's server traffic, transaction volumes, or sensor readings. With both trend and seasonality identified, we can apply time series decomposition, a technique that separates your data into its constituent components. Classical decomposition models express time series as a combination of trend, seasonal effects, and residuals, the random variation left after accounting for known patterns. By isolating these components, we gain powerful analytical advantages. The true power of decomposition becomes apparent when we focus anomaly detection efforts on the residual component alone. The residuals represent what remains after accounting for expected patterns. They're the unexpected deviations that might indicate genuine anomalies. By directing your detection algorithms toward residuals rather than raw data, you dramatically reduce false positives while improving sensitivity to subtle anomalies. This pre-processing approach transforms even simple statistical methods into surprisingly effective anomaly detectors. A basic z-score approach applied to residuals often outperforms sophisticated algorithms applied to raw data, simply because you've removed the confounding factors that create false positives. Here's where the magic happens. By systematically removing trends and seasonality before applying detection algorithms, you're essentially teaching your system what normal looks like at each point in time. That Monday morning traffic spike isn't an anomaly, it's an expected seasonal pattern. The gradual increase in system load isn't suspicious, it's a natural trend reflecting business growth. The preprocessing pipeline for time series anomaly detection follows a clear sequence. First, identify and remove trends to create stationary data. Second, detect and remove seasonal patterns at multiple frequencies. Finally, pass the residual component to your anomaly detection algorithm. This approach dramatically reduces false positives by ensuring that only truly unexpected variations trigger alerts. What makes this approach particularly powerful is its adaptability. As seasonal patterns evolve over time, perhaps your Monday traffic spike shifts to Tuesday due to changing work patterns, the decomposition model naturally adapts through ongoing retraining. It doesn't just capture static patterns, it evolves with your data's changing rhythms. Real-world implementations demonstrate the transformative impact of proper time series preprocessing. An e-commerce platform that implemented seasonal decomposition before anomaly detection saw false positive rates drop by 87% while improving detection of genuine issues. A manufacturing system using trend removal and seasonality adjustment detected equipment failures 3.5 days earlier than previous approaches by identifying subtle deviations in residual patterns. The benefits extend beyond accuracy improvements. Analysts spend less time investigating false alarms and more time addressing genuine issues. Detection thresholds can be tightened to catch subtler anomalies without drowning in false positives. And perhaps most importantly, your detection system gains contextual awareness about what normal means at any given moment. This doesn't mean simpler detection approaches are obsolete. In fact, the opposite is true. Proper time series preprocessing often allows simpler, more interpretable detection models to perform exceptionally well. A basic statistical approach applied to well-prepared residuals frequently outperforms complex deep learning models applied to raw data, with the added benefits of transparency and computational efficiency. Ultimately, taming time series complexity requires this systematic approach to temporal patterns. By decomposing complex time series into manageable components, you transform a near impossible detection problem into a straightforward one. Your system no longer needs to rediscover seasonal patterns with each new observation. It already understands the rhythms of your data. Now that your system understands the rhythms of your data, you face a crucial decision that many practitioners get wrong. Which detection model should interpret these carefully prepared signals? The architecture spectrum spans from lightweight statistical methods to sophisticated deep learning ensembles, and the gap between detecting 60% versus 90% of critical anomalies often hinges on this selection. Let's explore the architectural landscape that powers modern anomaly detection. Think of these architectural choices as different lenses through which your system views the data, each with unique strengths and limitations that profoundly impact what your system can see and what remains invisible. At the foundation of this spectrum lie statistical approaches, elegant in their simplicity, yet surprisingly effective. Z-score methods measure how many standard deviations a data point sits from the mean, flagging extreme values. For many applications, this approach works remarkably well, despite its mathematical simplicity. Imagine a manufacturing system where component temperatures rarely exceed certain thresholds. A Z-score detector efficiently flags concerning spikes without complex training procedures. Density-based methods like dbescan take a different approach by identifying clusters of normal behavior and marking isolated points as anomalies. These methods excel when your normal data naturally forms dense regions in feature space. A network traffic monitoring system might use dbscan to identify communication patterns that don't cluster with typical behavior, potentially revealing intrusion attempts that statistical thresholds would miss. Isolation forests represent an ingenious approach that turns traditional clustering logic on its head. Rather than trying to model normal behavior, isolation forests ask, how easy is it to isolate this data point? Points that require fewer random partitions to isolate are considered more anomalous. This approach proves particularly effective when anomalies appear as isolated points in sparse regions of your feature space, like unusual transaction patterns in financial data. Moving deeper into the architectural spectrum, we encounter autoencoders, neural networks with a fascinating property. These models compress your data into a lower dimensional representation before attempting to reconstruct it. When trained exclusively on normal data, autoencoders learn to compress and faithfully reconstruct common patterns. When presented with anomalous data, however, the reconstruction error spikes, providing a powerful signal that something doesn't match learned patterns. The autoencoder architecture creates a bottleneck that forces the model to learn the essential features of normal data. When an anomaly appears, perhaps a manufacturing component exhibiting early warning signs of failure, the reconstruction attempt fails in revealing ways. The higher the reconstruction error, the more confident we can be that we're observing an anomaly. This approach proves particularly effective for high-dimensional data, where simple statistical approaches would struggle to capture complex relationships. For time series data that we've carefully decomposed, forecasting-based approaches offer a compelling detection strategy. These models predict what should happen next based on historical patterns. When the actual observation significantly deviates from the prediction, we flag a potential anomaly. The elegant aspect of this approach is that the prediction error itself becomes our anomaly signal. No additional complex logic required. Consider a server monitoring system that learns to predict CPU utilization, memory consumption, and network traffic based on time of day and historical patterns. When actual measurements substantially differ from predictions across multiple metrics simultaneously, the system can immediately flag potential issues, often before they impact users. LSTM, long short-term memory, networks take forecasting capabilities to another level by capturing complex temporal dependencies. These recurrent neural networks maintain an internal memory state, allowing them to remember important patterns and relationships over extended sequences. This makes them particularly adept at detecting contextual anomalies, where a value isn't inherently anomalous but becomes unusual in its specific temporal context. An LSTM monitoring a patient's vital signs might learn that Heart rate typically increases briefly after medication administration before returning to baseline. A pattern that deviates from this expected sequence could signal a medication reaction even when individual readings remain within normal ranges. The power lies in understanding not just individual values, but their relationships across time. The performance differences between these architectures can be substantial. Basic statistical methods might catch obvious anomalies, but miss subtle patterns. More sophisticated approaches can detect nuanced deviations that simpler models would overlook entirely. However, this improvement doesn't come without trade-offs. As architectural complexity increases, we typically sacrifice interpretability and computational efficiency. Statistical approaches offer clear explanations. This value is 3.7 standard deviations above normal, while deep learning models often function as black boxes that provide detection without transparent reasoning. Similarly, lightweight methods can process thousands of metrics in real time on modest hardware, while deep learning approaches might require significant computational resources. The research reveals a fascinating finding. Ensemble models that combine multiple architectural approaches consistently outperform single model implementations. By leveraging the strengths of various detection strategies, these ensembles achieve benchmark performance with recall rates of 0.92 and precision of 0.82, significantly outperforming individual approaches. An ensemble might combine statistical thresholds to catch obvious anomalies, autoencoders to detect pattern deviations, and LSTM networks to identify contextual irregularities. This performance advantage comes from addressing the fundamental challenge of anomaly detection. Anomalies aren't all alike. Some manifest as statistical outliers easily caught by simple methods. Others appear as pattern deviations only detectable through complex representation learning. By combining diverse detection strategies, ensembles cover more types of potential anomalies. The decision between architectural approaches should be guided by your specific constraints and requirements. When explanations matter more than squeezing out the last percentage points of detection performance, simpler models may be preferable. When missing critical anomalies carries severe consequences, the computational complexity of ensemble approaches becomes justified. Consider how different domains prioritize these trade-offs. A financial fraud detection system processing millions of transactions daily might justify the computational expense of sophisticated ensembles given the high cost of missed fraud. Conversely, an IoT monitoring system running on edge devices with limited computing power might require more efficient approaches even at the cost of some detection sensitivity. The importance of matching your architecture to your specific data characteristics cannot be overstated. Time series data with strong temporal dependencies benefit significantly from LSTM-based approaches. High-dimensional sensor data with complex interrelationships often responds well to autoencoder architectures. Data with clear statistical properties might be effectively monitored using simpler approaches. Testing multiple architectures on your specific data reveals performance differences that no theoretical understanding can predict. The gap between models can be dramatic. The difference between detecting barely half of your critical anomalies versus catching nearly all of them. This performance gap often justifies the investment in architectural exploration and evaluation. Those high-performing ensemble models come with a hidden cost that many system architects can't afford to pay: computational resources. Consider the challenges faced by IoT sensor networks that must operate for months on a single battery charge, or real-time monitoring systems processing millions of metrics per second with sub-millisecond latency requirements. In these scenarios, the computational efficiency of your anomaly detection approach becomes just as critical as its detection performance. This is where the practical reality of deployment environments forces difficult trade-offs. That sophisticated ensemble model achieving 92% recall might be theoretically superior, But what good is it if it can't run on your target hardware, or if it drains your device battery in hours instead of weeks, or if it introduces unacceptable latency in time-critical applications? Fortunately, recent advances in lightweight model architectures have created alternatives that deliver surprising performance despite their minimal resource requirements. These approaches don't just scale down existing models, they fundamentally rethink the detection problem through the lens of efficiency. One of the most promising lightweight approaches is the LSTM-based forecaster with stochastic dropout. This architecture achieves impressive performance metrics, a precision of 0.74 and recall of 0.85, while requiring only a fraction of the computational resources needed by heavier models. The key innovation lies in its use of stochastic dropout, which serves dual purposes. During training, dropout prevents overfitting by randomly deactivating neurons. But during inference, the same mechanism generates stable confidence intervals around predictions without requiring ensemble techniques that would multiply computational costs. This confidence interval approach is particularly elegant because it allows the model to quantify its own uncertainty about predictions. When actual values fall outside these intervals, the system flags potential anomalies. The beauty of this design is that it achieves probabilistic reasoning capabilities, typically associated with more complex Bayesian approaches, but with significantly lower computational overhead. When even these optimized neural architectures prove too resource-intensive, dimensionality reduction techniques offer another powerful strategy. These methods transform high-dimensional data into lower-dimensional representations that preserve the essential structure needed for anomaly detection. For streaming sensor data with hundreds of metrics, reducing the feature space by an order of magnitude can dramatically decrease processing time and memory requirements without sacrificing detection capabilities. Principal component analysis, PCA, remains a workhorse technique in this category, projecting data onto a lower dimensional subspace that captures maximum variance. For anomaly detection specifically, the approach can be inverted, with deviations from the principal subspace often indicating anomalies. The computational savings are substantial. A model operating on 10 principal components instead of 100 raw features might achieve 85% of the detection performance while requiring less than 15% of the processing power. For applications dealing with truly massive data volumes, sketch-based algorithms provide perhaps the most radical efficiency improvements. These probabilistic data structures use approximate counting and sampling methods to process high-volume data streams with bounded memory usage. Unlike traditional approaches that must examine each data point exhaustively, sketch algorithms maintain statistical summaries that can answer approximate queries about the underlying data distribution. CountMinSketch, for example, tracks frequency statistics for stream elements using hash functions and a compact array structure. HyperLogLog can estimate cardinality, unique elements, with remarkable accuracy using minimal memory. These techniques enable anomaly detection systems to process millions of data points per second on modest hardware, identifying significant distribution shifts that would otherwise require orders of magnitude more computational power to detect. Another increasingly popular approach borrows from the world of deep learning optimization, model distillation. This technique involves training a smaller, more efficient student model to mimic the behavior of a larger, more complex teacher model. The process begins by training the heavy-duty ensemble model under ideal conditions with abundant computational resources. This model then generates predictions that serve as training targets for the lightweight model. The smaller model effectively learns to approximate the decision boundaries of the complex ensemble without needing to discover them independently through extensive computation. In practice, distilled models often recover 85–90% of their teacher's performance, while requiring just a fraction of the computational resources. This approach is particularly valuable when you have the luxury of training offline with substantial resources but need to deploy to constrained environments. The quantitative trade-offs between heavyweight and lightweight approaches are worth examining closely. While the LSTM-based forecaster with stochastic dropout achieves slightly lower performance metrics, precision 0.74, recall 0.85, compared to ensemble models, precision 0.82, recall 0.92, it operates significantly faster and with lower memory requirements. For many applications, detecting 85% of anomalies while meeting strict resource constraints proves far more valuable than capturing 92% but exceeding available computing power. These performance differences manifest in practical ways. A heavyweight ensemble might process 5,000 metrics per second on dedicated server hardware, while a sketch-based approach could handle 500,000 metrics per second on the same hardware. An LSTM-based forecaster with stochastic dropout might run continuously for weeks on an edge device battery, whereas a complex ensemble would deplete the same battery in hours. The question becomes, which scenarios justify accepting reduced detection performance in exchange for computational efficiency? This decision requires evaluating several operational factors. First, consider energy constraints. Battery-powered devices like remote sensors, medical wearables, or mobile robotics platforms have strict energy budgets that make lightweight approaches essential. When choosing between detecting 74% of anomalies continuously versus 92% for just a few hours before battery depletion, the former often delivers greater overall value. Second, examine latency requirements. Real-time monitoring systems in manufacturing safety applications might need to process thousands of sensor readings with sub-millisecond response times. When detection speed directly impacts the ability to prevent accidents or equipment damage, lightweight approaches that meet timing guarantees become non-negotiable. Third, evaluate scale economics. Cloud-based monitoring systems handling millions of metrics across thousands of servers face different constraints than single-device deployments. When computational resources directly translate to operational costs at scale, even small efficiency improvements can yield enormous savings. A 20% reduction in model complexity might translate to millions in reduced infrastructure costs for large deployments. Fourth, consider update frequency requirements. Systems monitoring rapidly changing environments may need frequent model retraining. Lightweight models that can be retrained quickly and efficiently on evolving data often maintain better long-term performance than complex models that become outdated between infrequent retraining cycles. The final decision framework emerges from these considerations. Accept performance trade-offs when operational constraints make heavier approaches impractical or cost prohibitive, or when the specific anomaly detection problem doesn't require maximum possible recall. Many monitoring applications can tolerate missing a small percentage of anomalies if the system operates reliably within resource limitations. Performance trade-offs may be acceptable when resources are limited, but there's a missing piece in our anomaly detection pipeline that no system can afford to ignore. When your critical infrastructure starts behaving abnormally across dozens of metrics simultaneously, how do you determine which one is the actual problem and which ones are merely showing the symptoms? Finding an anomaly is just the beginning of the investigation. Imagine you're monitoring a large e-commerce platform with hundreds of interconnected services. Suddenly, your anomaly detection system fires multiple alerts. Response times are increasing, error rates are climbing, and customer checkout completions are dropping. You know something's wrong, but which of these is the actual root cause and which are just downstream effects? This is where root cause analysis becomes essential. Root cause analysis transforms anomaly detection from a reactive alerting tool into a proactive problem-solving system. Without it, teams waste precious time investigating symptoms rather than addressing the underlying issue. In complex environments where components are highly interdependent, a single failure often creates a cascade of anomalies that obscure the original problem. Engineers call this alert storms, when dozens or hundreds of metrics suddenly trigger alarms, overwhelming operators with noise when what they need is clarity. The true challenge emerges when we recognize that correlation isn't causation. Just because two metrics started behaving abnormally at the same time doesn't mean they share a cause and effect relationship. This is why sophisticated root cause analysis techniques go beyond simple timing correlations to establish meaningful relationships between components. One powerful approach involves correlation-based analysis across multiple metrics. These methods identify groups of metrics that exhibit abnormal behavior simultaneously, helping to pinpoint related components within the system. By analyzing these correlations across a subset of monitored data, we can estimate which component likely originated the problem. For example, if database query latency increased just before API response times degraded, followed by a spike in error rates, the database might be the root cause, not the API layer that's generating most of the alerts. What makes this particularly effective is looking at both temporal and behavioral correlations. Temporal correlations examine the sequence in which anomalies appear, while behavioral correlations identify metrics that typically rise and fall together. When combined, these approaches can trace propagation paths through complex systems to identify the initial failure point. The metadata associated with metrics also provides valuable signals. Metrics with similar names or descriptions often represent functionally related components that might share failure modes. For instance, if payment processing latency and payment gateway errors both show anomalies, they likely point to issues in the same functional area. By leveraging these tech similarities, root cause analysis systems can group related metrics even without prior knowledge of the system architecture. This approach proves especially valuable in large dynamic environments where manual mapping of component relationships is impractical. Cloud-native applications with hundreds of microservices or containerized workloads can benefit significantly from automatic relationship discovery through metric naming patterns and descriptions. Another technique involves clustering metrics based on their typical behavioral similarity. The fundamental insight here is that metrics that usually behave similarly under normal conditions likely represent closely related system components. By establishing these baseline behavioral relationships, we can quickly identify when co-occurring anomalies suggest a common underlying cause. For example, CPU utilization, memory usage, and request queue length for a particular service might typically rise and fall in a coordinated pattern. When all three suddenly show anomalies, they form a natural cluster that points to that specific service rather than to unrelated components elsewhere in the system. These behavioral similarity approaches dramatically narrow the search space for root cause investigation. Organizations with sufficient historical incident data can employ supervised classification approaches for root cause identification. By training classifiers on labeled examples from past incidents, these systems learn to recognize patterns associated with specific types of failures. When a new incident occurs, the classifier can categorize the anomaly and identify its likely origin based on similar historical patterns. The power of supervised approaches comes from their ability to incorporate domain knowledge and past experience into automated analysis. A classifier might learn, for instance, that a particular pattern of database connection errors followed by API timeouts typically indicates a specific database configuration issue rather than a network problem or code bug. This historical pattern recognition can drastically reduce troubleshooting time. The most advanced root cause analysis systems combine multiple approaches into a comprehensive pipeline. One particularly effective architecture integrates correlation analysis, text similarity grouping, and supervised classification into a multi-stage process. First, the system identifies metrics showing abnormal behavior and groups them through correlation analysis. Then, it enriches these groups with functional relationships derived from metric metadata. Finally, if historical data is available, it applies supervised classification to categorize the incident and suggest likely causes. This integrated approach delivers remarkable results. Case studies have demonstrated that automated root cause analysis can significantly reduce mean time to resolution, the critical period between detecting a problem and fixing it, by implementing systems that correlate anomalies across multiple metrics. Organizations have achieved up to 70% faster identification of root causes, dramatically improving operational efficiency. The practical impact of this improvement cannot be overstated. For a major e-commerce platform, reducing incident resolution time from hours to minutes can mean the difference between a minor blip in operations and millions in lost revenue. For a healthcare system, it could be the difference between a quick fix and compromised patient care. Beyond the immediate operational benefits, effective root cause analysis creates a valuable feedback loop for the entire anomaly detection system. As engineers confirm or correct the suggested root causes, this information can be fed back into the training data for supervised classification approaches, continuously improving future analysis. This creates a virtuous cycle where the system becomes increasingly accurate over time. What makes this approach particularly powerful is its ability to adapt to evolving systems. As organizations add new components, services, and dependencies, traditional manual troubleshooting becomes increasingly difficult. Automated root cause analysis scales with the complexity of the system, making it an essential capability for modern operations teams. As powerful as automated root cause analysis can be in theory, implementing a system that remains reliable when processing millions of metrics in real time presents a different challenge entirely. Did you know that the most common reason anomaly detection projects fail isn't poor algorithm selection, but overlooking critical operational infrastructure? Building a theoretical anomaly detection model in a controlled environment is one thing. Deploying that same model into a production environment where it must continuously process massive data streams, adapt to changing conditions, and provide actionable insights to different stakeholders is an entirely different challenge. This operational gap explains why so many promising anomaly detection initiatives never deliver their expected value. Let's examine the critical implementation factors that transform a promising algorithm into a business-critical system. First among these is scalability, a dimension that becomes increasingly important as organizations instrument more of their operations. Modern environments generate unprecedented volumes of time series data that grow exponentially as businesses expand their monitoring footprint. This explosion of metrics necessitates architectural decisions that allow systems to scale horizontally rather than vertically. The most successful production implementations employ distributed processing frameworks that partition workloads across multiple nodes. These architectures distribute both storage and computation, allowing systems to maintain consistent performance even as data volumes increase by orders of magnitude, rather than processing all metrics through a single pipeline. Mature systems segment data based on priority, frequency, and complexity, with different processing lanes for different types of signals. An often overlooked aspect of scaling is the implementation of adaptive sampling techniques. Not every metric needs to be analyzed at its highest resolution. By dynamically adjusting sampling rates based on signal volatility and business importance, systems can dramatically reduce computational requirements while preserving detection quality for critical metrics. For instance, stable background processes might be sampled less frequently than customer-facing services where anomalies have immediate business impact. Even the most scalable system becomes useless if it overwhelms operators with a flood of alerts. Alert management represents the critical interface between detection systems and human decision makers, and its implementation can make or break adoption. The challenge here isn't just detecting anomalies, it's presenting them in a way that enables appropriate human response. Effective production systems implement sophisticated alert management strategies that go far beyond simple thresholds. These include multi-level prioritization schemes that distinguish between urgent operational threats and informational anomalies. Intelligent grouping mechanisms identify related alerts across different systems and services, collapsing what might have been dozens of separate notifications into a single actionable incident. This prevents the alert storms that typically occur when a single root cause triggers cascading anomalies across interconnected systems. Contextual enrichment represents another crucial alert management capability. Rather than simply stating that a metric is anomalous, production-grade systems automatically attach relevant context, historical behavior patterns, related metrics showing similar deviations, recent configuration changes, and potential business impact estimates. This transformation from raw alerts to contextual incidents dramatically improves mean time to resolution by giving operators the information they need to take appropriate action. No matter how sophisticated the initial implementation, all anomaly detection systems require continuous refinement to maintain their effectiveness over time. This is where feedback loops become essential operational components rather than theoretical nice-to-haves. Every alert resolution represents a learning opportunity for the system. Successful production implementations create structured feedback mechanisms that capture analyst responses to each detected anomaly. Was it a true positive or false alarm? If legitimate, what was the root cause? What action was taken to resolve it? This feedback then feeds back into the system through multiple mechanisms, adjusting detection thresholds, refining feature importance weights, updating classification models, and enhancing root cause analysis algorithms. The most sophisticated systems implement active learning approaches where the model explicitly requests feedback on specific detections to maximize its improvement rate. By intelligently selecting which cases to present for human review, these systems can achieve dramatic improvements in precision and recall with minimal human effort. Some organizations report reducing false positive rates by over 60% within 3 months through systematic feedback incorporation. Beyond technical implementation considerations, production systems must solve the interpretation challenge. Detecting anomalies serves little purpose if stakeholders cannot understand their significance and take appropriate action. This is where visualization and explanation approaches become crucial bridges between technical capability and business value. Effective visualization techniques transform abstract statistical deviations into intuitive representations that communicate both the presence and significance of anomalies. Rather than showing raw time series with threshold violations, mature implementations provide visual context, highlighting the expected range, showing similar historical patterns, and indicating the relative severity compared to past deviations. Interactive visualizations allow users to explore detected anomalies across different timescales and related metrics. For non-technical stakeholders, explanation capabilities matter even more than raw detection accuracy. Production systems implement explainability layers that translate statistical detections into natural language narratives. Instead of reporting that metric X exceeded threshold Y by Z standard deviations, effective systems generate explanations like website response time increased by 300% compared to typical Monday morning patterns, coinciding with the deployment of version 2.4.5 to the payment processing service. These explanation frameworks often employ template-based approaches augmented by machine learning components that select the most relevant contextual factors to include. The most advanced systems tailor their explanations to different user personas, providing technical details to engineers while focusing on business impact for executive stakeholders. When these components are integrated into a cohesive architecture, they create a system that's substantially more valuable than the sum of its parts. A reference architecture for a production-grade anomaly detection system typically includes several interconnected subsystems. At its foundation lies the data flow infrastructure, streaming pipelines that ingest, preprocess, and route telemetry data to appropriate processing components. This layer handles the mechanics of data collection while ensuring reliability through buffering, redundancy, and error handling. Above this sits the core detection subsystem comprising multiple parallel processing lanes for different detection strategies. High-priority metrics might pass through real-time detectors with minimal preprocessing, while less critical signals undergo more sophisticated batch analysis. The outputs from these lanes feed into a unified anomaly database that maintains the state of all detected deviations. The model training pipeline operates somewhat independently, continuously evaluating model performance and triggering retraining cycles when accuracy metrics drift beyond acceptable thresholds. This subsystem maintains multiple model versions simultaneously, allowing for controlled rollouts of improved detectors. The evaluation mechanism tracks both technical metrics like precision and recall and business impact measurements, such as incident resolution time and cost avoidance. By connecting detection performance to tangible business outcomes, this component helps justify continued investment in system improvements. Finally, the feedback incorporation subsystem captures human input across various interfaces and translates it into model adjustments, threshold updates, and knowledge base enhancements. This component serves as the learning engine that drives continuous improvement. As we've explored throughout this journey, the true power of anomaly detection extends far beyond the technical implementation. The most successful systems fundamentally transform organizations, enabling the shift from reactive firefighting to proactive problem solving. Organizations implementing these systems report significant improvements in operational efficiency and customer satisfaction by identifying issues before they impact the business. What makes these systems truly effective isn't just algorithmic sophistication, but how seamlessly they integrate machine learning with human expertise. The most valuable anomaly detection platforms don't simply flag deviations, they provide context, explanations, and recommended actions that empower teams to respond quickly and effectively, reducing downtime and improving decision-making quality. Remember that building your anomaly detection pipeline doesn't require perfection from day one. Start with the fundamentals we've covered. Define your baseline carefully, build a complete pipeline rather than focusing solely on algorithms, and design for your specific operational constraints. Even a modest implementation that embraces these principles will deliver tangible value to your organization and serve as the foundation for future enhancements.